Just to remind everybody, the topic today we are going to be talking this session is deploying VPNs over segment routed networks made easy. We're going to talk about the SDN approach, software-defined networking approach. As an introduction, my name is Krishnan Thirakonda. I'm a principal engineer in the SP routing and automation team, part of the what used to be called MIG. We are now called the provider connectivity team within Cisco. The scope is to help large-scale networks, be deployed to automation and operations made easy, right? So that's the approach. Crosswork is our, the product name, or let's say portfolio name that we have, in case you haven't heard of it. So this is a 1-hour session, but I would like to be in touch with you. If you have any questions, discussions, please consider joining the WebEx Teams through the Cisco Events app, and I'll be monitoring it. And if you want to set follow-on meetings, more deep dives, we can do that. So what I thought we would cover today, given the goal is automation and SDN, we probably need to start with a little bit of technology review. This is not by any means a deep dive into any of the topics on segment routing, SRv6. There are lots of sessions that are happening in this conference, which you should look into. But it's more like a flyby quickly so that we, when we go into automation considerations and the actual automation, we kind of, are fresh in our minds on what we are talking in this session. After the little bit of technology review, we'll go into automation considerations. What's new in the automation field, right? Automation has always been talked about. What do we mean when we say SDN, in this context? Then we'll switch to the Cisco's controller for transport SDN. Again, I'll explain what that means. And we'll not do a lot of slides at that point. We'll switch to a demo, right? So we'll go through that, and then we'll conclude. I do have in the slide deck that should be available already through the app a bunch of information that I'm not covering. I label them as reference, mainly to give you more background. In some cases, there are config examples and things like that. So that's for your reference and to add to more understanding rather than covering here in the interest of time. So let's get started with technology review. So when we talk about transport networks, we are really talking about your on your WAN network, wide area network. You're providing end-to-end services. Typically, these are either some kind of VPN, L2, L3 VPNs, RFC 2547 based VPNs with BGP, or your eVPNs, that type of technology. And then you have also your internet services. You may have multicast requirements. You may either in the VPN context, and there's so many flavors of multicast VPNs that you could be doing, or just global content delivery. All of those you can think of as transport service, because you're trying to connect on a large region or a wide area network, different sites. And then you want to give separation and all that you get from VPN, virtual private networking technology. Sometimes those are called as overlay services, because you're kind of overlaying each customer's network as a independent network, virtual network on a common MPLS, IP MPLS core. And then you have traffic engineering technologies. Used to be RSVPT was the one that was available till segment routing came out. RSVPT has been out for a while now, and some folks have deployed it. It's not deployed as pervasively as expected due to a lot of limitations of the technology itself. Segment routing solves a lot of them, right? So that's something to remember. And then with segment routing, there are two flavors really. One is using your MPLS core and running segment routing over it, which has been out for quite a while now, and a lot of adoption happening. SRv6 is a new thing. It was always talked about right from beginning, but SRv6, the way the segment labels were created, using IPv6 addresses was pretty, intensive on the forwarding planes. But now we have something called microSID, and there is a lot of debate and discussion on it. There was interop testing done at ENTC in the MPLS World Congress, and a lot of vendors now are supporting this microSID, a 32-bit compression of a SRv6 label. And that helps really a lot of hardware implementations cope up with this, large-scale label requirements. The expectation is a lot of greenfields will start adopting purely IPv6 cores with SRv6 for overlays. There seems to be a lot of interest in, at least in a few customers that are always IPv6 first. So when you create VPNs, you have to actually bind it to a traffic engineering policy, right? And this is, there are different tools in the traffic engineering tool set and to achieve this. And the main thing that you're trying to achieve is that for different VPN customers, end customers, you're trying to give them different service level objectives, right? A customer may want a certain type of optimized metric. Latency, for example, is a popular one. Or they may want some part of topologies either to be used, a sub-topology in your large network, or a set of links to be avoided, or things like that. That's why you're actually trying to use traffic engineering to avoid any kind of suboptimal path when you just use IGP routing, right? But to bind a VPN to traffic engineering policies, there are different techniques, right? So the classic technique is, and this applies very nicely to point-to-point services, virtual private wire services, is that you just take a point-to-point service and you say all of the traffic for this service should go through a tunnel, right, or a SR policy. And the configuration is actually done through iOS XR through something called preferred path, and then you give the RSVP tunnel name, or you give the SR policy name. So this is nice and simple because you have the packet coming in from the attachment circuit, you encap it with the VPN label, and then instead of putting an IGP label, you put the traffic engineering label, which is either a RSVP tunnel label or a SR policy label. But when you go into multi-point type of services, then it's a little bit complicated. For example, with L3 VPNs with RSVPTE, you would have to basically do like an auto-route announce kind of thing with all your loopbacks and build your full mesh of RSVP tunnels. But all VPNs would end up using the same set of tunnels. If you want to do differentiated services, then you have to do a little bit more configuration, and it can be cumbersome. For example, we have to create a different loopback per VPN, and then map that in the BGP next hop for that VPN using route policies, or you could use class-based tunnel selection, policy-based. There are different things that came out to support this. All of them are not as easy or convenient to deploy. But with segment routing, traffic engineering, we have this concept called on-demand next hop. So in segment routing, we have policies just like RSVT, where you say from head end to tail end, I need this traffic engineering constraints and objectives to be met, and you basically tie all of that to a color. We call it segment routing colors, right? It's basically a bit field integer that you can actually use. So you get a lot of policies between the same set of two nodes, router nodes, head and tail end. Each of them can have different colors, and each color is a different SLA, service level objective. But when you go into full mesh kind of scenarios and you want to do a lot of those, you may end up configuring a lot of these policies. To avoid that, we have something called on-demand next hop. In this, basically what happens is that on every head end, you just put a template saying that whenever a tail end signals to me that traffic to that tail end has to go through a tunnel, I create a tunnel on demand, right? And that signaling is done through a BGP color community. So again, this is a standards-based technology. It's not Cisco specific. So you basically use a route policy to color your routes, IP routes or VPN routes. As the head end gets them, head end will basically look at a template that matches that color and instantiate policies on demand to that tail end, right? So this makes it really convenient to deploy multi-point services where you don't have to, in advance, a priori create all those tunnels to all the possible PEs, and you let the egress PE sort of send the routes with the color community and you bring it up. And the more important thing is that those prefixes, VPN prefixes, when they're installed in forwarding base, you can auto-steer the traffic into those tunnels, right? So it's called on-demand next hop and auto-steering because there are really two different aspects to this. And this is really a router feature. All vendors are looking to support this now. And this makes it really convenient to deploy highly differentiated VPN services with traffic engineering. So let's again review what is traffic engineering and why we are using it, right? So I'll go through these. A lot of this is just a review. This has been discussed and kind of well-known for a while. Even with RSPT, we have been doing a lot of this. One of the main problems with just using routing, right? What do you even need traffic engineering? Is that all traffic will use IGP routing and may end up going to the same exact paths, right? So how do you optimize your traffic for different metric than just IGP cost, right? An example may be latency, right? So if you want to have paths that are lowest latency and you're not mapping your IGP cost to latency, but you're just mapping it to, let's say, the dollar cost of a link or distance, then you may want to actually use traffic engineering, where you say, my traffic for this particular VPN or this, you can steer any traffic into any SR policy or tunnel, should go over the lowest latency path, and that path may be actually consist of more hops than regular hops, regular IGP costs, right? So that's one of the main use cases. The next one is where I said, for example, you may have sub-topologies within your big, large core network where there are certain properties of those links in that sub-topologies or areas, and you want traffic only to pass through those links, right? And the typical example, easy to understand, is like highly secure links, right? Either using MACsec or appliances. There may be customers that want their traffic to only go through those links. How do you ensure that all the traffic goes in the context of those links, in the subset of those links in your network? And the way to achieve that is using a traffic engineering capability called Affinity. And Affinity is implemented by having a bit field which you mark on all the interfaces in your router configuration. That information is distributed through ISIS or OSPF and can be used for path calculation. When you create a SR policy or T tunnel, you can actually say that this should have affinity to this property, and it'll use that. Or you can also say it should not go through those. So we have both kind of logical conditions. Next one, very popular one, is a disjointness. And this is for a customer that wants has a highly available app which cannot tolerate, let's say, packet losses and is willing to pay a premium. They want to transport 2 copies of all the data through your network. And the only, to really make sense of this, you really need to make sure that the traffic never crosses the same link node or any kind of shared infrastructure, right? We call them as shared risk link groups. So you configure, for example, 2 links, they may look like totally different, but they go to the same fiber conduit or fiber cable, and that gets cut or catches fire, then you may lose that data, right? So there is a way to actually use traffic engineering to say that I need this traffic to actually totally go on disjoint paths, meaning totally separate set of links and nodes end to end, and that is achieved through traffic engineering as well. And the other one is bandwidth as a constraint. RSVPT had this concept called reservable bandwidth. And with RSVP signaling, you could actually reserve on every link a certain amount of bandwidth from a pool called reservable bandwidth pool. And this is important because you may want to have services that needs bandwidth protection, meaning it can't really compete with other traffic because of the nature of the application or the commitment to your end customer. So then you need bandwidth as a constraint, and then you need to find paths where there is bandwidth available in that particular pool of bandwidth, right? So this may not be your IGP cost. You may want to find bandwidth in a longer path, either for cost needs or to protect that bandwidth. So that is bandwidth as a constraint. And then there is an interesting optimization you can do where when you hit congestion at certain links, you can actually create what we call as tactical traffic engineering, meaning you're creating T tunnels or SR policies to bypass some issues that are cropping up, right? So you're creating on demand when you detect some condition, some bypass tunnels and injecting traffic, steering traffic through it to relieve congestion. It gives you some time before you can actually go and really add more circuits or bandwidth to those links. And what happens is that you create a bypass path policy or T tunnel, and you somehow figure out what pull some traffic into it. So that's one. Let's also review the path calculation. When you're actually building T tunnels or SR policies, you have to actually say by which hops or how do you want to create your paths, right? And in terms of traffic engineering, there are basically a concept of metric minimization. If you just use IGP, ISIS, or OSPF to find paths in your network, it'll always trying to minimize what we call as IGP cost, right, from router A to router Z. So that is one aspect. And then with traffic engineering, like I said, you can have alternate metrics. You can have latency, you can have something called a T metric, which is just another metric that you may want to use instead of the IGP metric. So it gives you different ways of creating paths. And then you have constraints. The constraints are things like disjointness or affinity to certain links, things are, with the segment routing, you can also have a constraint saying the maximum segment depth should not be exceeded. And if you have routers in the path that they actually announce their MSDs through OSPF and ISIS, so the path calculation engines can actually pick paths where the maximum segment depths can be honored. The way you do it typically is that you either create them by hand, meaning you nail paths up. That's called explicit, SR policies. Or you, in RCP, we call them EROs, right? Explicit route objects. And you basically say from head end to tail end, you go through these hops. You may give all the hops, or you may give just loose hops, as we call it. This works for some scenarios, but typically, when the path has an issue, when one of the hops goes away, then this policy will stay down. So what people do is they create the explicit path as a first option, but then you can always give second, third, fourth option, and those are usually dynamic. At some point you say, even if no policy is up, just use IGP routing, the fallback, if you will. Now, dynamic path calculations where you say what my intent is, right? Intent is basically saying, this is what I want the traffic to behave. You network figure out what is the best path for this, and that's called dynamic path calculation. So all the head-end routers and we have the capability to find paths using a criteria that you give. You say, minimize my metric, which is latency, and have affinity to a certain property, say secure link, right? And then the router actually, the head-end actually has what we call as T database. Every link in the network, the link state database that is distributed with OSPF or ISIS has also been extended with the IETF calls them traffic engineering extensions to ISIS. There's a T extensions to OSPF standard as well. And it's pretty well implemented. And now there is a segment routing extensions to OSPF and segment routing extensions to ISIS as well, right? So all of that is available on the head end. The one gotcha is that the head end can only see the TE data from its own OSPF or ISIS domain. In large networks, you tend to divide and conquer, meaning you create many ISIS domains, then you run either BGP between them or somehow you scale up, right? So in that case, then the head end cannot see any tail end up beyond its own routing domain. In those cases, we go to centralized path calculation, where the head end actually makes a call into a path computation engine. We call it delegated path computation. And then the centralized engine will do the path collection and feed it back, right? So this is important to not only increase the scale of the big network that you may want to span your TE tunnels or SR policies across, but also to help on the hardware forwarding information, the FIB entries that you can carry. Because now you don't have to know of all the possible tail ends in your large network in advance. And this is a problem on access routers and lower end routers. As you push your layer 3 edges closer and closer to the access, you need your lower end routers also to be aware of how to reach any possible tail end in your large network. And with this technique, what happens is that you actually don't know the path to your tail end. You can actually go and ask the centralized PC on demand, and the PC will calculate and push the path to you. Path provisioning. How do you create paths? You can go configure on the head end. That's something we all know, iOS and iOS XR, you can go do that. This is called PCC initiated, meaning the path computation client. Head end is a client in the centralized path compute model. And then the head end will actually make a PCEP. It's a protocol called PCE protocol to the path computation engine to get the path, right? But you can also use the PCE as a single control point for your network, and you can actually configure policies from any router to any router through PCE itself. In Cisco iOS XR, the PCE, you can actually go and configure on the PCE saying that on your PCEP peer router A, create a policy to like a router Z, and use this constraints and this metric, and you can actually configure it. In the reference slide, I do have an example of configuring PCE as well as on the PCC. The good thing with the PCE configured one is that we do have APIs, so you can automate things like creation of tunnels based on some triggers. So you can do closed loop automation and create, the congestion mitigation technique that we have actually uses that. So now let's switch to automation considerations, right? So when we talk about SDN, what we're saying is that we want to have a common, let's say, abstraction of the network through which we actually interact with the network, right? We always had automation where we actually have service turnup and service activation automation, then we had the assurance stack, and then maybe if you're doing traffic engineering, we had path calculation and things like that separate. But with SDN, what we're saying is that we want to have one entity that is aware of all the things, a VPN service, the traffic engineering, the path calculation, and then the stateful path calculation, meaning if the path changes, needs to change because of a topology change, it can also do that. And the big one is that when you think of a single controller that's managing a network and abstracting it, you need to be able to see what's happening on your network, right? So you want to see a nice topology diagram with all your VPN services overlaid as an operational assist, because your operations teams, you don't want them to have to log into each router by router. Rather, you have to have a single control point where you can actually see what's happening on the network. And then finally, also service health monitoring. So you have your services, you can see them, visualize them, and then you have service health monitoring, meaning what is the health of my service is automatically calculated. Typically what happens is the assurance stack is usually an afterthought, meaning you have your provisioning and turn-up automation, and then you have assurance stack, and somehow people have to feed the assurance stack enough information saying, oh, that sub-interface that faces that on that router belongs to customer A, and this sub-interface belongs to B, and a lot of it is done like multiple times because they're all siloed, right? The idea here is that when you provision a service, you want visualization capabilities automated, and also you want the service health monitoring automated. And then the bottom three things in this slide are basically talking about all the traffic engineering things you want, which is also to be integrated here, which is if a VPN needs a specific service level objective, SLO. SLA is the commercial agreement, if you will, and SLO is a technical objective of what we want to deliver for a particular VPN, right? So the SLAs and SLOs, if they have specific things, then you want an easy way of creating those policies. You want those policies to be kept honored even in the topology changing conditions, when a link fails or node fails, or if a bandwidth changes, if you're doing bandwidth aware policies, you want the policies to be automatically, without a human intervention needed, to be honored. And when that happens, visualization becomes more super important, because when there's a complaint from an end customer and the ops team needs to look and see what the path is, because these are on nailed paths, they're dynamically changing, you want to see what those paths are. So visualization is very important. And bandwidth awareness and congestion mitigation tool sets, again, this requires extra things to be built, and typically these are done as independent tools, but in a SDN concept, we want these to be integrated. Now let's look at, beyond just services, what other things we would need in terms of automation, right? It's not just service turn-up and monitoring, but we also want to have the full network lifecycle, if you will, network operations. Right from when manufacturer ships a product to your field and it's powered on, it needs to call in and get registered so it can be managed automatically, right? We call that zero-touch provisioning. There's actually an IETF draft, IETF standard, sorry, at this point, that actually is a let's say, multi-vendor approach, not a Cisco-specific approach that Cisco has also adopted on Cisco XR routers, and we are trying to support that on the Crosswork product as well. And once the product comes up, then it needs to have its configurations and images, not only on day one, but on an ongoing basis maintained. And then when you go to day two is where the service lifecycle comes in, which is where you're creating and deleting services and monitoring them. And a part of that is also collecting data for your long-term planning, right? So all of that needs to happen in the automation context, meaning you don't want to build separate tools for each of these, and you want one integrated view, right? Looking at service lifecycle in detail, there are really two areas you can split them up, right? If you look at the top part, this is where you're taking the order from an end customer, right? You're trying to figure out what type of service they want. They want an L2 VPN with eVPN, virtual private service, or an ELAN, E3, or a L3 VPN, and then what are their SLO, service level objectives that we are agreeing with them. What are the handoff points? What are the sub-interfaces, right? What is the IP addresses on the PEC links, and what is the routing protocol you're running? A lot of that requires interaction with customers, and there's always a human in the loop in that area, right? So that is one aspect of data that you need to collect from the customer. The second aspect is purely provider-based, right? As a provider, you pick, for example, route targets, the RDs, eVPN IDs, virtual channel identifiers. All of that, is automated with some policy saying, let's use this block for this, or any kind of internal policies. There are resource managers, IPAMs, and things like that that will be used here. And finally, what happens is that there is always some approval chain and authorizations, meaning once automation fills up some of this information based on policy, we want a human in the loop to actually check it and approve it before it actually gets pushed to the network, right? And that top part is basically all of that, and that's something you can think of as process workflow automation, right? So there are a lot of tools there. Those tools need to have a way of plugging into some ticketing system or approvals and authorization systems. And so that is really, that's why I'm showing that circle there. Now, the bottom part is the technical piece, which is once I know I fill in the blanks of all the things that I need to actually create the router configurations. That's the part that I actually want to delegate or to have the SDN controller do it, right? I'll make an API call to the SDN controller and say, here's my VPN, here are the sites where the customer attached, here are the interfaces that I've already determined works for this customer, here are the sub-interfaces, IP address I've agreed with the customer, here's the protocol I want to run, and then I don't want to worry about what are the device configs going to be for this particular service. I want the SDN controller to go figure it out. And also I want the SDN controller to create the traffic engineering policies. I want it to also start assurance, and I want to do any kind of health monitoring and send notifications outbound. If you have your SDN controller integrated with your ticketing system, it should send notifications that results in tickets, right? So that's the job of SDN controller. The point I'm trying to make here is that you can actually build your controllers, or you can have the Cisco vendor-built controllers here that are focusing on the technical bits, not on the human-in-the-loop bits. That's where the workflow automation comes in with your own IT groups or in-house developments, or using standard enterprise transformation logic applications, things like that. And the idea is you build your API calls, and the SDN controller needs to provide you abstract API calls. It needs to provide you an API call for doing an L3 VPN, right, or L2 VPN without worrying about what are the exact configs on Cisco XR or Cisco XE or any other vendor. The multi-vendor aspect also needs to be managed. So now let's switch to Cisco's transport SDN controller. So we had a disparate set of products. We had NSO, which is our orchestration engine. We have SRPC, which is an iOS XR feature that can do path calculation. But one of the things that came out is that it needs to be integrated as a one SDN controller product, right? So that's when we started on this journey to build this product called Crosswalk Network Controller. It's been a few years at this point. We are at 5.0. That's our shipping version of it. And just to recap what we support on it, we support provisioning of L2, L3 VPNs and all of the flavors of traffic engineering. SRv6 is a hot topic. We actually added a segment routing-based multicast transport called TreeSID, point-to-multipoint tree using segment routing in our latest release. So you can provision as well as visualize it on topologies. And I think one of my colleagues is doing a session just on multicast TreeSID here. We have a bandwidth awareness capability. We are supporting SR, IGP, flex algorithms, and local congestion mitigations. We are a stateful path computation engine, so we actually keep every state that we gave to head-end so that when the link topology changes, we can go and reprogram the head-end with a better path or more optimal path. And then the operational assist of visualization, path calculation, service health monitoring, network health monitoring, all of that is built in, right? We have a lot more, but in this, I'm going to focus only on the VPN and SRT paths, right? And again, the way it's built, like I said earlier, we did have always this set of products called NSO, which is our configuration engine, and we have the XR SRPCE. But this piece that we built, basically glues them all together, right? So you come from the north, you have a single interface into your network from the north, either through using the user interface or through the API, and then you actually configure services which actually gets pushed to NSO, or you create SRT policies using SRPCE. And then we have a very big data collection layer, which collects telemetry, not only for bandwidth-aware path calculation, which actually needs to know how hot your links are running and how busy they are, but also for service health monitoring. And we'll look at some of these components in detail, right? So like looking at just provisioning, we use NSO. Some of you may be familiar with NSO because it's been sold even separately as a network provisioning and orchestration platform. So what you do is use that to build your orchestration stack. It comes with a set of what we call as network element drivers that knows how to talk to each device type. We have about 170 types of devices, Cisco and non-Cisco, that we talk to at the bottom layer. And then this is the area which is extensible and field programmable, right? So the main audience for NSO as a platform is to development community, network automation developers, right? They actually fill in this part in a traditional NSO standalone deployment. But with CNC, what we have done is we have put in the VPN models, the VPN mapping code, and as well as segment routing. So you can actually just use the northbound APIs to create VPNs and traffic engineering policies. So that's the activation workflow. And then we have hooks into service health monitoring so that it's all abstracted from your point of view. Talking about path control, it's basically a feature set on our iOS XR. Right? You can run it on any of your iOS XR routers, NCS, 5500s, ASR 9Ks if you want. Typically, though, it's run as a virtual machine because it's a pure control pin element. And the reason to run it as a pure control, as a VM is because then you can throw more resources at it, right? It's a x86-based, computers. You don't have to, have an expensive hardware to run it. But it can also run on any of the hardware if that's the, more convenient to run. And it's basically a stateful PCE. It's actually multi-domain, meaning when you have lots of routing domains, it can run BGP link state protocol, which each of those routing domains to pull in the link state database. BGP link state, if you're not familiar with it, was just an optimal way of distributing anything that OSPF and ISS already has to give it to an application server that uses it to do something, right? Now, those applications can also be in ISIS OSPF, but it was deemed to be not convenient, not secure, meaning it could potentially feed back. But this BGP link state is a read-only protocol, meaning all of those routing domains, one or two of the routers can run a BGP link state, and that will take everything in the ISIS OSPF DB and send it over BGP. It's one way, meaning the application just consumes it. It's not going to push anything back. That's how we know of all of the link state and TE database on the SRPCE. And then we run PSEP protocol. So again, this is a standards-based protocol, so we can work with any other router, vendor router as well. And basically, this is where you're creating paths, right? So path requests and path updates and things like that. And then for the telemetry, which is bandwidth aware, you need to collect telemetry, and that's the part that we are doing through SNMP, right? And we do it through now in the latest release GNMI. And for that, we actually need another component because the Cisco router XR is not really optimized to collect massive amounts of data and store them, right? So that's the piece that actually comes from, I'm going back a little bit just to show you that it comes from this component here. It talks to data collection layer, and it talks all standard stuff. One thing to note, all the interfaces to routers are very standards-based. And NSO can handle translation to any types of devices on netconf CLI. So that's why we claim that we can support a lot of multi-vendor devices. A lot of the deployments, initial deployments, are actually happening on multi-vendor networks on large SPs, service providers. So at this point, I think we can switch to a demo. On service health, I just have one slide. So service health actually is a kind of an innovative approach. What we are doing is that when we create services through a model-based approach, I'm not sure what happened there. There we go. We have all the data in our configuration DB on what the service intent is. It's an L3 VPN. It connects to these 4 places. And then we actually internally do the translation of device configs. At the same time, we can do translation to the KPIs, key performance indicators for that service, health of that service, right? For example, if you know this sub-interface faces the customer, we can do a show interface on that interface to collect its history. We can collect counters on that to see if there are packet losses and things like that. We can collect any IPS-RA TWAM sessions, Y1731 metrics that we can also configure, and we present all of that in the service health dashboard for that service. So this is what we are implementing on Crosswork as a service health mechanism, which is very service aware. It starts from the service configuration and calculates the KPIs and does it automatically in advance, meaning you don't have to go and do it after the fault occurs. So you actually usually get to see the problem even before the customers see. We have actually documented this in an IETF draft called Service Assurance for Intent Networks. The hope is that we can make it more broader than just Cisco. All right, so now let's go to demo. And in this demo, what I'm going to show is basically how it looks on CNC. So let me switch to this. In the interest of time, what I did was I actually recorded it, and I can actually talk through it as we go. So the first part of the demo is going to talk about visualizations, right? And then I'll show how to create a SRT policy using Cisco Crosswork. In this visualization, I want you to understand that even if you don't use Crosswalk for anything else, you can just use it for visualization, and that's a really big value add for a large network, complicated network. So let's go get started with this. So here we'll show 3 types of paths, disjoint path in the bottom, low latency, disjoint, and bandwidth constraint. So this is the dashboard of CNC, and here you can see basically that all the services and traffic engineering related items are in this tab called, services and traffic engineering. And then if you go into traffic engineering, I've already created those policies, so that we are going to look at visualization first. This is auto-detected, meaning if you have these policies created on the router and you have a PC running, we can actually detect that and show them here. And then the left side shows you the topology that also we have auto-detected based on, auto-discovered based on the BGP link state we are running. And then you can enter the GPS coordinates and we can render it nicely on a map. And once you have this, all the links that we detect to BGP link state, we can do SNMP or telemetry to get all the link usage, right? Those colors are indicating that the links are running hot, or green means like below 10%, or red could mean 50% or higher occupancy, yellow could mean something. You can actually configure those so that you can actually very quickly see how busy your links are running. Now this is important even for bandwidth related features in the system, but also for visualization. So if you go pick the 2003, which is basically an SR policy running from 5 to 4 to 3, here you see the path that it will go through, right? So this path was created to optimize on low latency. When you click on it, you basically see hop by hop paths that this policy will go through. And if you click on the 3 dots to view details, here you get the details that you can actually log into the router and do show segment routing traffic in color 2003, and whatever detail you get there, you can see it here. So the idea is that you shouldn't need to actually log into the routers to see this kind of information. And anybody that is in ops, some of them may not even have access or permission to log into routers, but they can still access this. And you can see there's an adjacency SID followed by node SID. Here's the intent. This is latency optimized path, right? So all of that you can see. So next, let's take a look at a disjoint path example. So 20,051 and 20,052 are examples of between the same 2 nodes in this particular topology, disjoint, right? So you can actually see that it's actually going through 2 different paths. And if you go into any one of them to see the way we have specified that they should be disjoint, this is actually the convenient part with dynamic path calculation, right? All you need to do is that if you pull down the path criteria, you see that there's a disjoint group ID and association source and type. So any LSP or SR policy that has the same values will be kept separate by the network. The user doesn't need to think anymore about which hops should I use. You just specify that that groups should all be separate. Next is an example of the bandwidth on demand. So in this case, 777 and 778 are between the same 2 nodes, and they're all asking for bandwidth. So bandwidth on demand. And the bandwidth reserved, this is a very small 10 megabits per link XR9K CML-based network, so 1 megabit, right? So now if you come back and ask for a second path, 778 color, with the same 1 megabit, and the system is tuned to maximize available bandwidth, it'll use totally different set of links, as you can see here. The blue ones are the second one that came in after the purple one, 777 came up. So this is an example of how we can do bandwidth management. And if you go in the second one, you will see that we are also doing bandwidth on demand. And the system is basically optimizing the max available bandwidth, right? There are some knobs and things here saying that go with, I'm going to pause here, go with metric first, then available bandwidth. And those are all settings on Crosswalk that you can do. So this one, what we're going to do is, now we're going to create a policy just to see how that is done, and we're going to create using affinity, right? So the policy intent is going to be that use only the links that have a property called secure link. In this lab, there is no MACsec, it's all XR9Ks, but this is just to show an example of how you would do a path that has to use, let's say, only MACsec-enabled links in your network. And then we are going to use a color called 2004. We are going to go from 4 to 5 and 5 to bidirectional policies. In TE technology, there's something called TE attributes for every link, and it's a bit field of 256 bits. Each bit means something to you. You can actually configure that bit 10 means this link has MACsec, right? And that's what I did. And then you can say when you create a constraint, you can say pick only the links that have bit 10 set, right? So let's see how that actually works. So let's let it run. And I'm going to show this using Postman, which is an API also. So here's the first part. So if you see here, this is basically how you actually configure on iOS XR. First, you configure an affinity map saying secure link is bit 10 is secure link. You're giving a textual representation to bit 10 to remember what it means. And then you put certain interfaces that have that property as affinity to secure link. So this is let's say day 0 config, right? And then we go back, and then now we try to configure on the UI. So for configuring, you go to provisioning. NSO is used, so that's why it shows provisioning NSO. Here you see all the things we can do. We have L2 VPNs, we have L3 VPNs, we have RSVPT, and then we have segment routing. So in this case, we are going to go and create a policy under segment routing. So you can go and click plus. It's a form-based interface for creating the policy based on the SRTE model that we built into the system. But behind the scenes, NSO, if you're familiar, NSO is what is doing the work. There's a Yang model for SR policies, and we're rendering this form, and you can actually go through this form and fill in this information. And then commit it, right? That's how we would do it. But what I've done is that I'm going to show you a shortcut where I can actually load a JSON file into the UI to create it, right? So I'm going to click on that little icon there, and I'll load a file that has the entries for the UI already filled in. And this is the same thing that you'd use to make API calls, right? So now it fills up the UI with the same set of information. We are going to create a SRT policy with that name, going from node 4 to node 5's loopback IP. And then we have a set of candidate paths. We only have one in this case. We're going to do a dynamic path calculation. And then if you open that, you'll see that we are actually going to delegate the path calculation to PC. That checkbox says that. And then we have one constraint saying that we want affinity. All links should include this property called secure link, right? That's all we need to do, right? And before this config gets pushed to the router, we want to see what that config is. So for that, we have a feature called dry run. And here's where CNC will go and do the path calculation and say, this is the net new config that's going to be changed. It has this plus and minus to show what's going to be removed, what's going to be added. And then you can see here that here's the config that's going to be pushed. And the bottom part is the device agnostic config. They look very similar in this case because the SR policy model is very similar to how the XR config looks. But this is what we're going to do. So you can close this and go ahead and commit. At this point, it's actually going to connect to the router and actually configure it on the router, right? So this is happening at this point. So it takes a few seconds because all of that logging in and configuring it takes a few seconds, right? And this is just one router, but if you think of a VPN with 10 routers, 20 routers, how many ever sites, they all will be configured at the same time. Now, if you go back to traffic engineering and you see a list of policies, you will see that 2004 has showed up. And if you click this, you'll see the path. Now, I artificially created a zigzag path so that you can see that you actually can use traffic engineering to achieve this, right? So you can put affinities for any kind of policy that you have, and then you can create policies, SR policies, and then you can inject traffic. That's how you get fine-grained control using the affinity tool set. Now, this is another example of creating, for the reverse path from 5 to 4, I'm going to use a tool called Postman. It's an API test tool. Some of you may be familiar with how to test APIs with Postman. And it's basically REST API. So we're going to do a patch. In REST, there is get, post, patch, put, and delete. Those are the options. And then it's based on HTTP, HTTPS. And the payload is the same file that I loaded on the UI. It's a JSON file, and you will see very easy description. JSON is very easy to read. You can also do XML if that's what you want to do. And then when you're ready to click it, you can click send, right? So this Postman is basically an API test tool, so it's going to make an API call into Crosswork and push this payload, and you'll get a success or failure. This is what, if you go back to the slide where I showed workflow automation, the workflow automation people, if they're your own IT folks, they're going to develop this, they're going to use Postman to check whether they can actually create services. So that's why I'm showing you this, that once you have validated all the services you want, and you know what type of service you're going to create, and you're happy with from the technical point of view, then you can actually work with your integrator for anything that you have already from the business workflow or anything that's you want even more broader automation, right? Either you can use it as a UI-based thing for yourself, or you can have further automation built on top with your ticketing and process workflow things. So this is just showing you that anything you can do on show segment routing traffic engineering is all available here. Here's a delegated PCE that actually did the path calculation, and here's the constraint that you can see here, right? We are actually going to constrain, the bit 10 is also shown here because the textual thing is actually mapped to bit 10. End of the day, that's what the router knows. So, yeah, so then you can see all the segments, node segments, all of the information is really relevant. And then if you go to the router, let's look at the configuration that came in on the router. So show configuration commit changes last one on the router gives you the whatever last commit was done on the router, right? You can see exactly the config that we pushed on the head-end router. And this is an example, this is exactly what we created through crosswork, right? So it went and configured. And then you can get the operational state here. This is typically how you would do it if you didn't have a tool that would grab it. The point I'm making here is that you don't have to do this, log in and look at it. You have it at your fingertips. We can just click through, and not only you can see those segments that this policy is going through, but you can have it shown on a topology diagram, which really is useful for network engineers because you're really thinking topology in a visual fashion, right? And you can see those segment identifier labels. Those are the labels that are going to be used for that policy. So next, we'll switch to the next demo. This is going to talk about L2 VPN visualization. And this is going to show you that we can visualize. I've treated the VPN already. And so this is a visualization we have. If you go to provisioning, you will see that under L2 VPN, there's just exactly one. And in interest of time, I already created it. When you click it, you see this kind of, it's a point-to-point service. So we are just showing the two Ps that participate in it. And we are saying it's a VPWS service. You can get more information by clicking on overlay. We actually have some SDKs where you can take anything in the payload that you put in, decorate the UI, right? So we do have, and this is a payload that was used to create it, right? It's again a JSON payload. You could either drive this through API, or you can save this as a file and import it to the UI. And this is a targeted LDP type of VPWS, so you can see the virtual circuit identifier, you can see the attachment circuits. This is the JSON file that you can give it to anybody who wants to make calls on crosswork. There is no transport here yet. I'm not bounded to any underlay transport like SRT or RSPT yet. The reason is I want to show that even in that case, if you want to know what is the path packets will take from, say, node 5 to 4, we can actually go and do a trace route on demand. When you click path query, which is a label that you see on the side, we actually go and filter the set of nodes that are participating in the VPN, and then you can choose which direction you want, node 4 to node 5 in this demo. And then when you click get paths, it's actually going to make a call to the node 4 to go do trace route SRMPLS multipath, and it's going to dynamically doing it, and then it's going to render it on the topology, right? And you can see the results. It's nicely showing to you rendered on the topology, so you actually can visually see what path packet will take for this particular VPN service. And the output of show trace route is also shown here. So that's another very useful troubleshooting aid. Now what we'll do is we'll go and modify this policy to actually use this 2004 color affinity-based SR policy we created, right? So let's now go ahead and do it. So we can go and do edit here, and then we actually can go to the UI, and I'll just show you in the UI where this is specified. By the way, this UI structure is painted using Yang model for L2 VPN, which actually comes from IETF, right? IETF is kind of standardizing some of the service models, and here's where SR policy or RCBT can be specified. But to save time, what I'll do is I'll make an API call. Once you get hooked onto using APIs, it's really convenient because you don't want to type a lot of stuff, and you can just use APIs. And again, this is on node 5 and node 4. We're going to say when traffic goes from node 4 to node 5, use that SR policy, and from 5 to 4 and the other direction, use the other policy, right? So this is the structure of that API. So that bit is getting augmented, let's say, to that VPN config. And then when you send it, it's going to connect to the crosswork and push this payload, and you'll get a 200 series, which is basically a good return code. That's basically your REST API. If you go to the router and look at what got pushed, show configuration commit changes last one, you'll see that we got preferred path SRTE, and then the policy name came in. And then fallback disable means if the policy doesn't come up, disable the whole L2 VPN. VPN will go down, right? Some people prefer that the policy stays up and uses IP routing, but you do have a choice here. So now let's look at transport tab here. And the cool thing now is that we know that you created a VPN and you bound it to a VPN, to a SRT policy. We can go filter out those policies and show in the context of the VPN, right? You're still in the VPN view. And the transport, now we show that there are two policies that are actually bound to this VPN, right? And you can click those and see the path that now the traffic will take, right? You don't have to do the path query anymore because now we know exactly which path the packet is going. So that's the convenience of having binding and visualizing it together. Here's another example of L3 VPN with a dual SLO. There's a lot to read here, but basically what I'm trying to show you is that this L3 VPN customer wants two treatments. Some traffic should be low latency with, as a provider, I decided I'm going to use color 4003 for it, and some is best effort, so I want to use color 4001. And in this case, I'm going to use ODN templates, meaning I'll have an ODN template for 4001 with IGP metric and an ODN template for 4003 for low latency metric. I do have to create prefix sets to map customers' prefixes to these colors, and then I need to create a route policy. So let's go ahead and see how that works. So provisioning, and then you go and first I'll show you that I've already created those prefix sets. There are a few prefixes from customer that will be mapped to prefix set name, right? And then I'll have a BGP set extended community thing here where I'm going to set the actual color community. And if you go to policy, this is where you will see that we are binding them together. The first statement says anything matches prefix set with the name, with the 4001, set the color community 4001, right? It's basically using the power of RPL, route policy language in iOS XR. And then what we do is that now we create an L3 VPN to use all these route policies. And in this case, I'm going to load the JSON file that we would use on the UI. So let's go ahead and see that. And now I can show you a few examples of things on the UI for L3 VPN. For example, we are creating a full mesh, any to any. You can do hub and spoke, or you can do custom import-export of route targets if you want. If you go under VPN node, this is where all the PE sites which are participating in the VPN are. It's a 3-site VPN, node 3, node 4, node 5. And then under the VPN route target, you have the actual values of route targets, right? And then we can do dry run again to see what will be the change that will be pushed to the network. And this is where we're going to calculate the change for node 3, node 4, node 5. And then you can see them here, right? This is, again, you'll see VRF getting created. You will see the export policy being applied. You will see the PC subinterface, the BGP, and here's a route policy, and this is how it will look on iOS XR, right? So that's what we're showing here. And once you commit it, it'll actually push to the routers, and then now we can go and see how it appears on the router. So it does take a few moments because it's going to connect to each router and push it. Let's see if it came on node 5 already. So yeah, so this is, if you are familiar with iOS XR config for L3 VPNs, you can see that we are creating a VRF, we are applying export route policy that we created. We have the definition of the policy in the same config. We have the PC link here. So the route policy with the extended community set. So basically what we're saying is whenever the customer advertises those prefixes, we're going to add extended community and put it on VPN v4 so that all the other PEs get it with that. And those PEs, when they get this customer routes, VPN v4 routes with that color community, they will look for an ODN template, which actually I already created, right? So if you go and look at show run segment routing traffic on demand for a particular color 4003 or 4001, you will see those templates are created. 4001, again, to remind, is going to be best effort. 4003 is going to be low latency, right? So they are already created, put in place, and I actually created them using CNC as well, right? It's actually created, if you go down here, you see there's ODN templates, and I have those two. I've created them, again, to save time, it's already there. So now let's go back and look at visualization, right? If you go back to VPN services view, you have L3 VPN here. It showed up, right? And then you can go inside and see this is how it looks on the screen. L3 VPN, we show all the PEs that participate in this VPN. We label it as a multi-point service with L3 VPN, and you can actually see the route targets that are import-exported by clicking extended overlay. If you have very fancy import-export, hub and spoke, you can also show that here. If you go to transport sub-tab on the right, you will see now that a full mesh of SR policies came up without doing anything. We didn't configure the policy, we just put the route policy and the ODN template, and the routers themselves brought up those policies. And we are able to go filter it and show it in the context of VPN. So that's the main value in the visualization, is that in the VPN context, you can see from a site to like node 5 to node 4, which path will it take, right? Because we said low latency, it's going through that specific path. And you can get all the segment routing, traffic engineering details by clicking on view details in the same context. So again, this is just showing you an example of how to do more fancy granular SLAs for a particular customer, right? Let's see. Now we want to go and do, if you go to traffic engineering, you'll see that these extra policies, 4003, also got added. If you remember, we didn't have that before. We got a 6 full mesh policies got added. This was created specifically for this VPN. The last part is looking at service health. Let's see. Let's go take a quick look at that. So service health monitoring, we are going to enable service health monitoring for the L2 VPN that we created and the L3 VPN that we created. And then we'll see how it looks on the screen, right? So for L2 VPN, I already created it before I recorded it. For L3 VPN, let's see the mechanics of creating it. So first you pick either basic or advanced. Basic is a very simple monitoring. Advanced is more flexible. Let's look at advanced. And then we have something called SLA profiles that you can pick gold, silver, bronze, where we actually compare against metrics. It takes a few minutes, 5 to 10 minutes for building state. The L2 VPN one is already running, so let's go into L2 VPN. And you can see that there are no symptoms, everything is good, we are reporting, right? In terms of what we are checking, we call it an assurance graph, meaning it's the graph of dependent things that feed into the overall health, right? So it may be hard to see, but there's a number of things we're checking, starting from the attachment circuit, going to the show L2 VPN cross-connect state, which basically checks your target LDP session is up or not. And all of that's done automatically in advance and periodically, meaning every 5 minutes we go and collect this whole set of things using telemetry, and we paint the overall state so that when something fails, you know where exactly what component failed, right? And you can actually tie this together with overlay synthetic data testing with IP SLA, Ethernet SLA, OAM using Y1731 and get it. So now let's look at L3 VPN. In this case, we actually have a symptom of something failing. So let's look at the symptom. It's very textually descriptive of what the problem is, right? It's saying all the eBGP sessions on that particular VPN on the VRFs are not up, right? So in this case, I don't have any CEs connected. In a real life deployment also, you may configure the VPN and wait for the customer to bring up their CE side BGP session. So in that case, you will see this kind of alarm going on. And then you can go into this scenario, this assurance graph view, which tells you for L3 VPN, what are the things we're checking out of box. You can zoom into only the failure because in this case, for every site, the CE is down, so you have one. And if you look at all, you see we are checking a number of things, right? So that's why the zoom in feature is really helpful. The other helpful thing is you can go and look at history, because we can keep a history of all these alarms that are coming out for a service. And you can see that we keep up to 60 days worth of symptoms, meaning whenever we report a problem, we keep the history. And then you can actually click one of them and actually see what did we use to check, right? So if you see the BGP session state, they are shown here. And you can click on the little icon here, and whenever we report a problem, for the last 24 hours, we keep the raw data. So you can look at the raw data for the BGP session that it's flapping up and down, right? So that's my demo. So let me actually switch back to the PowerPoint to lead to conclusion. So basically, these are the things we saw. I'm available here to meet with you all, meet the engineer. I know we ran quite to the end, so we didn't have a lot of questions and answers. My colleagues are in the DevNet area if you want to stop by and look at what they're looking at. We have 3 controllers that are coming from the same team: Crosswalk Network Controller, the APIC controller, and the Nexus dashboard. And they're doing surveys on what are your opinion on how it should look and feel, right? So it's more of a user experience research topic that's going on. Here are some sessions. Some of them are today. If you want to have crosswalk related topics you want to look at, it's in the PDF. Again, I'm available on the WebEx team, and if you want to talk to me. Please do the survey so we can fine-tune our content, and I believe there are some gifts to be won. And then, yeah, these are standard slides. Again, I'm available here to talk to you. I know we have like 30 seconds left, but if any questions, anything that you want to ask, I'm here, and I can stay back as well if you want to have any further discussions. Thank you.